tectonics, salt structures, and the interaction between salt-controlled structures and sedimentary systems. And so we want to see how he's going to show us some new things that deviate from the classic, some natural examples from an analog models that deviate from classic salt tectonics models. So whenever we can get any research that takes us from the classic models, we're always interested to learn something new. So we look forward to your talk, Dr. Z. And so without wasting much time, Dr. Z, please take it away. Dr. G, sorry.
No worries. Thank you. So I'll just start sharing my screen, I think.
Say again?
I just start sharing my screen and
yes, please.
Talk, right? Good.
Yes.
Okay, I'll go back to summary then. No, not summary, the first front page. Right, let me just my pointer. Can you see my laser pointer? Good?
Yes.
Okay, good. So thanks. Thanks AAPG for inviting me for the talk. So today I'm going to talk about some work we did in Potsdam using analog models. So the topic is revisiting classic models. And this is not my own work, but also with Matthias, Michael, and Rob. So we did it together. And also we thank the funding bodies for financial sponsorship that allow these studies. So first, global importance of salt-bearing classic margin. So we know that well, the recent salt revolution really started in Gulf of Mexico, where you have lots of exploration goes on, and you have lots of subsurface data sets. And if you look at global distribution of these passive margins of basins, and you can see that this is Gulf of Mexico, and this is South Atlantic, this is Brazilian margin, and this is West Africa margin. All these margins are really oil rich. So these basins are not only interested for scholars, but also for industry as well. So things of tectonics in passive margins. I mean, I think the thing has been going for like a few decades. If you look at like papers in the early 1990s, you can see these classic like extensional faults in upslope, contractional faults in downslope. This is from Gulf of Mexico.
Sorry to interrupt. Oh, sorry.
Yeah.
The sound is a bit low.
Okay.
Are you using your microphone? Sorry for interrupting.
Okay. No. I don't know. Let me check. I don't know if I actually should I. Is it better now? Is it better?
I think still the same.
Let me see.
Are you using your?
Let me do that. Is this okay now?
Yeah, I think we can try and see if it's better.
I think I have to adjust to the setup.
Yeah, we got some feedback from the audience. So, if you can speak slowly, yeah, louder if possible. Okay, thank you so much, Anna.
I'm not sure. Where should I adjust my sound?
I leave you to continue.
Okay.
Yeah, it's better now.
Better now?
Yes, it's better.
Good.
Thank you.
Good. Okay, sorry. Thanks. So I just go back then to my screen. All right, and go back to my pointer. Yes. So no. Yes, right. So this is from a model from paper from Team Julie, like published 3 years ago, and so the essence of the model has been maintained, I would say, for the last 2 decades. You have this upslope extension, downslope, or slope contraction with middle slope translation, and such a system can be captured or reproduced by analog models really like perfectly well. So this is a very simple setting. You have this layer of sand, and you have silicon, the viscous material to simulate salt underneath, and when you tilt it, you have upslope extension, downslope contraction. And you can find similar systems in the nature, and this case is from the lower Congo Basin. However, when we look at nature, or we try to compare these basins, and they're quite different. So these are some profiles from the South Atlantic margin. You can see overall they're rather similar. So you can see this upslope extension, downslope contraction. But we look at detail, they're actually quite different. For example, here the salt being most driven into the toe slope area, but here you have lots of salt trap in the middle. So such variation, people try to explain such variation being proposed like, so there's two different types of gravity-driven failure. This is a classic model or figure from Ron, I would say. So this is the gravity gliding dominant system. Here, the whole thing is being driven by the margin tilting. So you tilt your margin and you have extension upslope down, and contraction and downslope. Or you could have just a gravity spreading system where you have a predominantly a progressional wedge or sediment driven system. But you also have to get this extension and contraction, upslope and downslope. I should mention that there are different views on how we divide these two types of gravity-driven failure. So there's a proposition that we use soft flow to divide them. For example, when you have this collapse flow or this shear flow dominance, you have the gravity gliding, and you have this Poissonian flow or channel flow dominance, you have gravity spreading. And Frank proposed another way to divide these two systems, that using the release of energy. So you have a parallel release of energy, you have gliding, and you have a release of energy that's perpendicular to the base, then you have spreading. I'll just follow this more widely used scheme here because it's actually quite easy for us to model system if we use these models to discuss things. So since we have these two different types of gravity failure, people like to identify them, particularly in nature, and it will help us to make these conceptual models more practical and useful. The one important diagnostic feature for the gravity spreading system is like this migration of extension and contractional domains. Essentially, you have this wedge propagation forward or basinward, and as your wedge propagates, your extensional domain propagates with it, and ultimately the wedge reaches in the area where being previously contracted. Now you have extension occurred on the contractional structures, and these features have been thought to be diagnostic for gravity spreading systems. So there are other works. This is from Leo. So it identifies two different types of gravity-driven deformation. So I think Leo used different shapes of growth wedge here. So we have this extensional growth wedge or propagational wedge, and you can try to correlate them to the nature. I think one thing that we can actually identify these two systems is because they have different controls. So my thought is, so how these controls, for example, you have a thermal substance here and the tectonic uplift here for gravity gliding dominant system. So we have differential loading, sediment propagation, gradation for gravity spreading dominant system. How these factors actually have their impact on the gravitational failure or on the margin evolution, apart from those diagnostic features we just talked about. The first, we focus on the gravity gliding dominant system. So previously, it has been modeled like many times. And so previously, it been modeled like use margin tilting as an instant tilting. For example, you have this model from Fox et al. 2004, It's also a classic paper, where you can see this model that you have extension contraction. And this model being simply tilted like instantly. So from start, you have 5 degrees of tilting. And there are also ways of tilting. This is step tilting. So this is too dramatic because in nature, don't really get 5 degrees of tilting over your margin overnight. Maybe we use this step tilting. Essentially, it's just a lot of small steps or small instant tilting. Well, in nature, all the margins in tilting like gradually. So you have this substance curve. We get some substance curve from the global passive margins, and you can see the all like go smoothly from 0 to some depth. So we designed our model like following the trend. So we have this instant tilting in a run, and another tilting, a progressive tilting, another run. And we do it for models designed like this. So essentially, we have a silicon basin here, a double wedge shape, and we have a this is a panel that we actually have 2 silicon basins, so we can actually model 2 different models in one run. The only difference between the 2 model silicon basin is one have 1 millimeter per kinematic layer, the other has 5 millimeter per kinematic layer. I'll just show you the results from 1 millimeter per kinematic layer model because the 2 are essentially similar. So how we apply progressive tilting is actually quite simple in a way that we just put a motor here. So the model being pushing gradually. So for instant tilting, we have 3.5 degree tilting instantly. And for the progressive tilting, we actually tilt it like 1 degree per day and lasting for 3 days and a half. We also adjust our modeling material, try to maintain the density contrast between the overburdened brittle layer and the silicon, because sand is usually too heavy for this kind of density ratio. And this is time scaling. So we run it for 5 days, or convert to time scale, roughly about 30 million years. And we see every 12 hours during the experiment. So we save like 10 times altogether. So this is modeling results. This is surface strength, and yeah. So I should tell you. So this is instant tilting. This is progressive tilting. We're looking at the model 1, where you only have 1 millimeter per layer, and this is the color scheme is important here. So when you look at the warm color, it will be extension, yellow or red. When you look at the full color, blue, there will be contraction. When you look at the figure, so this is time. So it's the first hour, this is around like the second day, the end of the third day or something. So it's time evolution. When you look at that, I think one very prominent thing is you have overall very red color here in the instant tilting, and it's actually gradually shrinks. Well, in progressive tilting, your red area actually at first relatively small, while it expands a bit. And it's actually more clear on the profile. So this is profile from the middle of the model. So this is cross section basically, and we extract the profile or the strain evolution along the profile and we plot through time. So this is time. This is from day 1 to day 5, and this is basically the profile. So essentially, we have like I think the interval is 1 hour. So we have lots of profile here. And together with cross section, it's actually very powerful. We can actually see that these are the structures you see observed from the final result. Well, this is the evolutionary profile. So by doing this, we can actually trace these structures to where and when it occurs or it starts. And it's obvious. So in instant tilting, you have really large area extension and area retreats gradually. You only have really like upslope area, like continue to the end of experiment. While in the progressive tilting, the extension goes in the other way, I would say. First, you have really small area, and it gradually grows, and you have new faults, extensional faults or grabens initiate. So this area is like going from small to large. So what it means for basin evolution. So this is a profile from I think it's from Lower Congo Basin. And so this is a seismic profile implication. So basically in progressive tilting, what you have is you really have growth strata in the later stage. While in the early stage, maybe the growth is not very prominent because your fault is not there yet. And from the subsurface profile, we can sort of observe similar things. So if you look at the most active faults, you can see the growth pattern from very early stage. So looking a bit downslope area, you can see the earliest growth strata is not very prominent. And what's the implication for brittle viscous coupling? So when we also look at it, so we want to explain why you have this large area extension effect and it gradually shrinks. So we check the velocity. You can see in instant tilting, because you have lots of energy. So Frank is right? You have lots of energy, and because you have like the highest gravitational energy, it releases, so you have the highest velocity. And as that energy runs out, the system slows down. While in progressive tilting, because you give it energy gradually, your system starts to accelerate gradually, and it more or less like peaks when the tilting stops, and then it goes down, similar to the instant here. The thing I want to mention here, because when you have such a system, you have very high velocity at the beginning. And because the coupling is strain dependent, so this is a model. So this is an extension model, but the explanation is the same. So when you increase the strain rate, the coupling becomes stronger. So for simplicity, you can think of water. If you put your hand into water really slowly, it's really soft. So you press it really quickly, it's really hard. So when you have this high strain rate, your coupling is strong. So you have wider area extension. Then, because your velocity slows down, it shrinks. Well, it's the other way around in the progressive tilting. A quick summary. For the gravity gliding, we conclude that margin tilting gives fundamental control on thin scales of tectonics by providing the energy, but also by deciding the tilting rate, because how you tilt your system actually controls how the system deforms, the speed is deformed. So margin tilting is really important for the coupling. So naturally, so we want to look at the other system, explore the control there. There are lots of models. This is a very famous one from Kinematic in 1998, where they modeled, I think it's a propositional delta something. Wherever, so if you have this wedge shape, propositional wedge on the silicon, and you have deformation. And there's another one from Bruno Vanderbilt, 2005. And on the first look, it's rather similar, right? You have extension and contraction, fine. But we look at detail, I'm not sure if you can see that. This system here, or the wedge here, is rather tabular. So if we look at the nature, I think it actually correlates well in nature definitional slopes. So there are also two types of definitional slopes. One propositional type definitional slope, which is usually less than 5. But actually most of them are very gentle, like less than 1 degree. Another is so-called bypass system or bypass deposition slope. It's usually larger than 5, and it could be like anything between 5 or 30. So it's upper limit is around 30 degrees, like Gilbert delta, something like that. I think this is from Lower Congo Basin or somewhere, I don't remember. But this is from an Arctic basin. I think this type basin you can see it almost everywhere because it's depositional and positional wedge. So with these two deposition slopes actually have some different implications in analog modeling. So we look at literature, there are actually some discussion lists. So there have been some use of wedge tape theory for understanding or to analyze the stability of these wedges. So what we have been looking at is here, the gravitational spreading. This study, although they mean that their study, but it's the same for our study. But they have some fluid components in their model, and they so we adjust them. We plot the stability wedge here. So it's actually quite simple in a way that. So you have this basal slope. So this is the surface slope. It's the basal slope, and any wedge within the slope is stable. And above it will be extensionally unstable, while below will be contractionally unstable. So we plot two numbers, like 5 and 27 degrees. Well, this is not a random pick, but they correspond to our model design. But when plotted, it's actually quite clear. The 5-degree one is just on the verge or the edge of this stability or critical slope. So it's on the edge of deform, while this green dot is really deep into extensional unstable domain. So it should deform really well. So we design a model very different from other models. So what we really focus here is the front slope. We want to produce these two kinds of depositional slopes. One is very gentle, less than 5 degrees. We pick 5 as a top. Another is very steep, 25 as starting point. Because we want to maintain the two models and we want to compare them. So we design the model in a way that so it has the same propagation rate and aggregation rate, so that the height and or the length of the model is the same. And we want to have different front slopes. And here in the model 1, you have initial slope of 5 degrees, and it gradually decreases upwards. So it's always in the domain of, or on the edge of this critical slope. While the model 2, we design the model so it's 25 to 27 degrees, and I think it increases gradually. So it's increased even higher. It's higher than 30 degrees or something. So I think this is something we did differently from previous models. We only care about the front slopes, and we because we want to compare the models, we fix the propagational rate and accretion rate. And okay, forgot to mention other settings will be exact same as the previous one. So we have this silicon basin, I think, more or less the same. And because we have two silicon basins, and because this time we don't use tilting, so we can actually run two models in one setup, which is great. So exactly same looking figure. This is surface strain. So this is we're looking at model 1 and model 2 surface from above this time. Oh, did I mention that these are from the IC cameras? So we have a monitoring system. You can actually shoot pictures for these models, and we can calculate. I should probably put at least one slide. So these are the model surface evolution, basically. Yeah, my fault. So again, the color scheme is really important here. You need to know colors, extension, contraction, which is great. So if you look at the red color, you can see the blue color goes forward. So you have the extension domain continue to deform. You can see the graben 2 is always there. And you have this front moving or migration contraction. So you have your extension and translational domain as a result. Well, here, when you have a non-stable or very steep slope, okay, so the time is similar. So this is from day 1, this is from day 2, this is day 3 or day 4. And when you look at it, it's quite different, right? So you have very close, the extension and contraction, they're really close to each other. And they move really fast. So both of them migrate forward really fast. And as a result, because your extension migrates further, the early extensional domain gets deactivated, and your early contraction domain gets extension. And same, so it's exactly the same type of profiles. So you can see contraction and extension. And so you have extension here, contraction here. So it's very clear. Here you have extension, rather like longevity system that it continues to the end. You do have a newborn extension of graben here, but you it doesn't really like go any further. While the contraction domain goes really like gradually as your system progresses, it goes further and further. So this is model 2, where you have this very steep slope, and you can see this 2 types. I heard a beep, but is there any problem? No? Okay. Or time is up. I think we actually have some time. So okay, yeah. So the system is really different. So we look at color. Color tells you instantly, right? So you have extensional domain continues to migrate and continues to shut down, and your contraction continues to migrate. So your early contraction gets inverted, and you have extension. I remember this is exactly so-called diagnostic features we would love to observe in nature, and this is we observe here. We can actually produce, but this is not really new because it's been produced before. So we also did something interesting this time. Michael did some flow analysis. So we use a surface strain, and we assume the surface strain here is shear flow, so the collapse flow, and we calculate them. Calculate both collapse flow and Basins flow. This is basically the instant velocity or in the silicon. Later we'll see a more detailed flow analysis. But when I look at the 2 types of wedge, remember that the only difference will be the front slope, but then they have the same propagation rate. So the front is always the same, and the height is always similar, the same, but the height is, yeah. So when you look at the distribution of silicon flow, it's actually quite different. So the model here, where your silicon flow is really like everywhere in the basin or under the wedge, so it's more evenly distributed. While in model 2, where you have a steep slope, you look at the color really focused to like under the wedge toe area here. And if you look at the OR velocity analysis, so the 2 types of wedge produce really different type of silicon flow. In nature, will be soft flow, of course. And we also look at surface velocity. So the blue will be model 2 or the steep slope 1. And so the overall velocity is like we thought, right? So you have a really high steep slope, and it has a really faster surface velocity. So it deforms faster. And you can also see, so this is the real-time velocity. So every time we put some sediment in, it deforms faster. You give it energy, it runs faster. No big deal. Okay. But then we look at the silicon flow velocity as well. So this is model 1, blue model 1. Yes, red green is model 2. And interesting, really, the Basins flow. So a collapse flow takes around here, around 40 hours, similar as the whole model. So for some flow really takes late, like around 80 to 100 hours, somewhere there. And remember, we have the same propagational rate. So this is exactly the time when the front wedge migrates somewhere there, where you have very, because we designed double wedge shape of silicon basin. Remember to have the thickest silicon here. So it's obvious when you migrate to the thickest silicon area, your channel flow is easier because the drag boundary effect is smaller. So this is why your channel flow peaks rather late when you have the thickest silicon in the system. Now, so this is our model, but as I said before, these models have been run many times. Although the boundary conditions are very different, so we really focus on the front slope. Well, but they have some similar examples. So this is from Kinematic 1998, where they started a very gentle slope, but later the slope is really steep. I think it's over 20 degrees or something. So again, you can see these very concentrated silicon flow. Well, this model from 1998, it has 5 degree propagational slope. And at starting point, you can see the even distribution of silicon flow. And we plot these models. So when measure it basically directly from their model, from the profile, because we don't really have many information sometimes like materials. So we just assume other conditions being the same. We plot them on our stability analysis. Really important. You can see here actually. So you can see the plots. So these plots are here. Okay, but so you can look at the green one, green square. So it's here. So it's on the verge of critical slope. But the ones here deform really fast or really strongly deformed are the ones deep in the instability domain. So in a way that these things actually being modeled before, it's just people didn't realize that they have different types of silicon distribution because they have different types of front slope. So this is from flow point of view, but we also want to see a similar basin evolution in nature, right? So this is from Levant Basin, and I'm not sure if you look at it, you can see that this is very long life box, so it's still active, and you can see very gentle slope. You see some of contraction, and it's also saying some of the migration contraction, but it's not that clear. But I want to mention that even in this profile, this basin, they have some margin tuning. So it's not pure gravity spreading system or gravity or wedge-driven system. They have some components of tilting, but again, it captures what we see in this model. So this Leo must be familiar with this because this is from his paper. So this is an extension. So we start seeing some of the like traces of folding. We're not really sure, but you can see early extension, sort of early extension, early folding here. And we think it's typical for steep slopes. But then come back to that. So I'm not how do I say it? So we have diagnosed features, right, for the steep slopes, but I'm not sure if you remember, I mentioned in nature, predominant depth slope will be the gentle one. So this kind of slope system or sedimentary wedges are more there. This system is quite typical to upslope extension, downslope contraction. And this is from the gravity guiding domain system. So you have upslope extension, downslope contraction, and you have gradual you have this gradual expanding the extensional system. So summary two is that so the wedge-shaped geometry exerts control on gravity spreading. And natural sedimentary systems predominantly have gentle slopes. So differentiate gravity spreading and gravity gliding can be inherently difficult. So some conclusions or rather thoughts. So I think gravity driven soft-techniques are fascinating. And the conceptual models, they are really good actually. So they're really well established. There are still many unknowns, and we can still explore how these systems behave using more realistic and more geological meaningful boundary conditions. And of course, we need to run more models. Right, thank you. And these are two main references if you want to check. Right, I'm a bit too fast, sorry. Okay.
Okay, great. Thank you. Nice presentation.
Thanks.
Yeah, so if you do have questions, please go ahead and type them in the Q&A box if possible. And let's see, I think we already have a question in the Q&A. Okay, first question then, from Mark Rowan. Nice and important work. What would be the impact of a different initial setup without the hinge and then landward dipping base salt? And then there's a next part. What if you have an outer trough with significantly thicker salt and an abrupt basinward edge? Step up onto oceanic crust. Basically like much of the Gulf of Mexico and South Atlantic. Thank you, Mark.
Thanks, Mark. And yeah, I think at first that's a really good question, because what we want to approach here is using modeling, analog model technique, but we really want to approach to reality. So we actually, maybe I didn't mention this, but we actually thought about this, right? So if we look at this, let's see, so there are actually two curves, right? One is 1 degree, one is 0.1 degree. So this is the basal slope. So because we actually thought about this, okay, because we realized that it's silicon thickness has an impact on your flow. What happens? Will it actually impact your stability analysis? Because it impacts your stability analysis or our stability analysis very strongly. Then we have to run our model with different setups. But then luckily when we so basically Matthias basically so there's 10-fold difference on the two base slope, right? If you look at the stability area, it's actually quite stable. So more or less like, okay, there's some difference, I would admit, but not that drastic. So the basin shape, well, it will play a really important role in your silicon flow, but it seems doesn't really affect the wedge stability that much. We think that the wedge stability rather or predominantly controlled by your surface slope. And the second question, yeah, I don't really know. I mean, we could design similar models to do this. I mean, you have yeah, I know what you mean. You have a very basic stuff in the toe slope, so will system behave differently. From purely from our point of view, from the slope analysis, I think the wedge, as I mentioned, because the silicon thickness or basin shape doesn't play that important role. So stability analysis, I would say, will largely stand. But then the detail evolution will be definitely different because your silicon flow will be different, right? In a thick salt area, your silicon flow faster, your percent flow goes faster. So yeah, it will be different. How different? Yeah, we need to run more models. All right.
Okay. Yeah. Thank you.
That answers.
Hopefully, yeah. Feel free to type follow up if you'd like. No more questions in the chat. I will.
There is one.
Oh.
From Susan in the chat.
Oh, sorry, I was looking at the Q&A box.
It's okay. Yes.
Okay. 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 Oh yeah. Okay. Yeah.
Is it this one? Are these extension/compressions at the base?
But I'm not
yeah,
sure.
I think this was on what the slides where you showed the model evolution through time. Maybe if we go back to those slides. That also relates to a question I had as well. Yeah, those slides, yeah. So maybe you can just explain, how the extension and the contraction is represented through time.
Okay, right. So you have to look at in another way. You should not look from down to up. You can look upside down. So you look at it. Okay, extension. You can correlate to the graben, right? And can trace it back. And can say, okay, here the graben really starts. And if you put it here, okay, the graben really starts here. This is how you use this plot. I'm not sure if this is the question, but that's it. So you can see, for example, this fold, this is better. There's this fold here, right? So it moves not that much, but actually initiates somewhere there. So you can trace all your structures back to space and time, and that's why I said this kind of plot is really powerful. That's why you can see, for example, this thing, right? Contractional on extension. It really starts here. So it really starts somewhere there.
Yeah.
Right?
Okay.
So looking this way around.
Suzanne said that question was actually meant for the top-down view of the models. Sorry, so I put you on the wrong slide there. But
okay,
before we move to that one, I'll just ask a question because I had a question that related to this one. So with the showing how the extensional domain widens or migrates through time. Actually, my question was more for the first part of the talk where you did the model on instantaneous tilting or gradual tilting. But I was going to ask, did you try to collate information from natural salt basins to see if we do observe this kind of widening of the domain versus narrowing of the domain through time, and which natural examples those two cases could relate to?
Well, first, relatively shouldn't have this kind of system, right? They don't have like 5-degree tilting margin. So if you look at these things, I would really like interested to know where you find it. But these things should be like you find it in most margins. And I think I talk to people in industry. I mean, I think the one thing is related to the normal fault, because when you're crossing the fault, you cannot trace the horizon, right? So what? It's normal, right? If you have a fault there, it's very difficult to trace. But as I said, if you look at those, I mean, and there are also some but in the paper we actually point out some examples. We think we observe such things like here. So this is a real seismic interpretation, but they didn't really interpret it that way. We realize here, okay, the early growth package in that there is much minor if there's still some compared or insignificant compared to these things. And if you look at a scale, it's only like 10 to 20 kilometers away. But that's not very large. So most salt basins or pessimized salt basins have such lengths, and they should behave like that, right? But we need to, in a dreaming world, I would have like 2 wells, one here, and I'll have all H information, one there, and all H information, and there will be like nail this down, but I don't have that. So
yeah, no, that's interesting. Yeah, because you can use the growth strata, like you said, to support that. Okay, so back to Suzanne's question then. Sorry, Suzanne. It was a question for the top-down view of the models, actually. So yeah, this slide.
Okay.
So just clarifying, I think, the extensional and contractional colors.
So this, so the extension will be red, right? And it's in upslope. That's why I think it's actually easy to look at this. So this is upslope, this is downslope. Okay, yeah, my fault. Okay, so I should mention. Okay, I should mention this. So we tutor the model in this way, right? So we tutor the model in this way. So you have this long wedge. So it's double wedge shape, silicon basin. So long wedge here. Maybe it's not that obvious when you look at the surface view, but it's very obvious here. So you have a long wedge.
Yeah. Okay.
I'm not sure if I answered that. So yeah. So I actually put like upslope edge, downslope edge here. I didn't mention that. I should do that. Sorry.
Yeah. No, that makes sense. Thank you. Hopefully that answers your question. So another question then in the chat from Webster Moriak. From your experiments, can you address if there is a control of the base of the salt horizon on the development of predominantly synthetic and antithetic fault systems?
Right. I would say that I don't think we can address that, because what we observe in our system. So the first is quite simple, although they look rather different, but you can look at them. So they really start because they have extension. So you can see these as the final result. They really start as a dipole or as a extensional graben, a very small one. So, and you have faults on both sides, so they really graben-like, but then they become asymmetric later. So yeah, you can actually trace them, but you can see, for example, this one is a synthetic, this one is antisthetic, right? And you have both here. So I'm not sure if I can address this, because the silicon thickness is varies because we have this wedge shape, so it's different everywhere. So talking about silicon thickness or base of silicon control on the synthetic and antisthetic fault is a bit overreaching for our setup. It could be done if you have a flat one, right? Then you can play with your model and to see it actually has some impact on your fault direction, but not probably for our setup. Sorry, our model has limit, right?
Right. Yeah. Okay, we have another question from Catherine Giles. For your steep margin model 2 scenario, would these typically be carbonate systems that mechanically would deform differently than siliciclastic systems?
Yeah, so in the paper Ross et al. 1992 and 1994, they're actually talking about those over steepening margins of slopes. So I think they present 3 types. One is tectonic, but then if I have a fault there, it's not only one, right? But yes, the carbonate is definitely one. And let's see the third one, and I cannot remember exactly what it is, but I can send you the reference. It's Ross our S 1991. It's on geology, and they're talking about this adjustment of slopes, because before that people think most of slopes are really gentle, but they suggest there are some of slopes that are really really steep. Yes, carbonate definitely is one, but I think I remember the third one. I like Gilbert delta, but that's maybe probably too small. But that's the reference we should look at.
Okay, yeah. Related to that, then, on the 2 models that you showed that had the different angles of the progradation, since you say that most of what we observe in nature is actually very low angle slopes, because that's all
natural system. So actually, okay, yeah. So natural system. So if you have a tectonics, right, it will completely like tectonic control. We have the natural system more because it's stable, right? Makes sense. Yeah. So what's your question? Sorry.
So I was just going to say, do you think the difference that we've seen between the high angle and the low angle model, since most of what we observe in nature is actually these low angle progradations, do you think that the angle of the slope would actually have a significant impact in most, or an observable impact that we would see in most salt basins? Because I guess it would be quite easily overprinted by all the other factors that you have going on in salt basins. So I guess it's not always easy to identify the impact of the angle of a prograding wedge when you also have complications from basalt relief and other aspects.
Yeah, that's a really good question. Actually, in the paper or in the preprint, you actually discuss it a bit. So you're quite right, because in nature, right, you always have mixed sedimentary system, right? You have like gentle slope, it may become steepening, or it become like very steep. And actually, it happens in the central space on where you see this. I found one literature, and I also cite that in the preprint, that actually they actually find really like steep translational slopes that really promote to turbidite. like around 10 degrees, up to 10 degrees in the central basin. Well, in the other area, so this is the famous Alvin Gap area, right? In the other area, we don't really find that very steep slopes. So I think you're right. It's very difficult to distinguish because the signals are always being buried in all kinds of other signals or other controls. But we can sort of like so maybe like if you find something in central, it looks really like seems like sedimentary driven. Maybe you can go back to look at your deposition profile. And if you really find a lot of very steep slopes, then maybe it's a hint that your sedimentary system really plays an important role in driving these systems. Maybe.
Yeah, sure. Yeah, it is complicated. Yeah, always complicated. That's why salt basins are fun.
Exactly.
Let's see. So we have another comment from Mark Rowan. I'm not sure if this is a question or just a comment, but we all need more data to test these models. The evolution of extension is fairly well constrained due to proximal positions, lots of wells, etc. But the timing and patterns of contraction are less well known due to more complex structures, overlying salt sheets, fewer well controls. Yeah, so I guess that also links into the complexity of trying to relate these processes to natural salt basins.
Yeah, exactly. That's why we also feel so the setup is actually quite untraditional, or so it's done really like because people like to have something. Okay, these two wedges looks too different, right? And we just really want to know if it actually plays a role. And Mark is really right that we don't really know too much about contractional domain. And I would say that comment is great. Yes, we always would like to have more data, but the deep water area is always difficult because there's too much salt there. They don't really have a good reservoirs.
Yeah, we'd always like more data. That's always true. And sorry, I've just seen the question was whether these numbers of extension and contraction that, on this slide that you were just on. Sorry, go back to the top-down models.
These are numbers.
The slide, on these. So the question was the numbers, are they measured at the top or the bottom of the salt body for the extension and contraction?
Yeah, the top of the surface of the model. So what we always only have the ability to model what happens like here. So we have a camera to take the picture. If we have an X-ray, like you did in France, maybe you can do some more cool figures, but not this one. Sorry.
Yeah, that makes sense. Yeah, just clarifying because I managed to butcher that question twice already. So hopefully that was what the actual question was. Okay, I can't see any more questions in the chat or the Q&A. So if that's not the case, then I guess we just thank you for a nice talk and allowing us to think a bit more about physical modeling and these classic models of salt tectonics that we have for passive margins. So thank you.
Thank you for the invitation, and thank you all the audience as well for the questions.
Okay, great.
I really enjoyed it.
Thanks, Zhiyuan. It was really good.
Yeah, and we have next webinar is next week. So we're doing, we have a few in quick succession at the moment, but yeah, we'll see you next week. Thank you, everyone. Okay, bye. Have a good day.
Bye-bye.